So let's take a look at an example. Let's compare Euler's method to improved Euler's method and see that it performs better for this equation, dy dt equals negative 0.4y, with y of 0 being 100, our initial condition, and we want to compare these two processes at time 4. Now this is fortunately a separable differential equation, and if you were to solve it and evaluate the initial condition, you'd get 100e to the negative 0.4t, and you have to use x here. And this just shows me that at time 4, I expect my y value to be at this exact value, 20.189652. All right, so standard Euler's method. To do the standard Euler's method, let's start with that one, just to recall what this looks like and how this works. So we calculated the slope, which is given by negative 0.4y. And because our step size here is 1, we don't really need this column, but remember delta y is the step size multiplied by whatever that dy dt was. And I'm going to write dy dt as f of t comma y. All right, so this guy here, another name for him is f of t comma y, and that's just convenient because we can see what values get plugged in. So here we have 0 and 100 for our starting value. And if you take negative 0.4 of 100, you get negative 40. Now because our step size is 1, we're going to multiply that negative 40 by 1. Remember, that's a decrease of 40 elk per year. And we are going to advance 1 full year. So this is going to be negative 40. Again, like I said, we don't really need this column. So that means I'm at 100 elk. I expect to lose 40 elk, so that's going to be at 60. And now we'll repeat this, negative 0.4 of 60, which comes out to negative 24. Okay, and so again, I'll take 1 unit of time, negative 24 units per unit of time, which is negative 24. And so now that 60 is expected to decrease by 24 in 1 year, which comes out to 36. Taking negative 4.4 times 36 gives me negative 14.4. And again, 1 times that will give me negative 14.4. 36 is expected to decrease by 14.4, which is 21.6. Here we'll get negative 8.64, and same thing here. And so at time 4, my estimate using the standard Euler's method will be 12.96. Now, that value of 12.96 is not at all close to what we had expected of 20.19. So our relative error is quite large, or percent relative error, which is my estimated minus my exact, divided by my exact, multiplied by 100 to get it into a percent, comes out to negative 38.84%. Holy mackerel, that's huge. That's a huge error. And as a result, we wouldn't want to use a step size of 1. Now this is fairly common with Euler's method, so nothing unexpected has happened here. But now let's go ahead and carry out the improved Euler's method. So for this method, we want to lay out a very similar table. Keep in mind we're going to have a step size of 1 still. I'm going to create a few columns here because the second slope can be a little challenging to lay out at first. And I think by having more columns, it makes it a little bit easier. So what we want in our columns, of course, t and y. And then I am going to have a couple more columns in here. And remember that with improved Euler's method, we're going to compute 2 different slopes. One is going to be at our current location, and the next slope is going to be at our next location. So what that means is I'm going to use this slope right here to get me to my next point. Okay, this is my next point right here, t k plus h, y k plus h times the slope. Okay, Okay, so this is my next point that I get, and I'm going to compute the slope at that location. So I'm going to use, at my current location, generate a slope. Then I'm going to use kind of basically Euler's method to get my next point on that curve. Now with Euler's method, t1, y1 would be the point we'd use, but instead what we're going to do is we're going to compute the slope at this point right here, and then once we have that slope, that's our k2, we're going to average these two slopes together, come back to t0, and then use that new slope to carry us to a new point at time 1. So here's what this is going to look like. So first of all, we are going to compute we're going to compute k1, which will be f of our current t, and I'll write it like this, t, k, y, k. So that's just our, k just stands for our current position. So times 0, we know our initial condition is y equals 100. And we know that our differential equation is negative 0.4y. Okay, negative 0.4y. Okay, so this one only depends upon the value of y. So once again, what we're going to get here is negative 0.4 times 100. That's going to give us the same slope of negative 40. Now what I want you to picture is what we've just done is at time 0, here we are up here at 100, y equals 100. We have just determined that the rate of change is negative 40. Okay, so if we project that into the next unit of time, if we went to time 1, well, that would put us at 60. Right? It would put us at the point 1, 60. So what I'm going to do is I'm going to create a column here, and these are going to be my helper columns. This is going to be my tk plus 1. Okay, tk plus 1, remember, is our current t plus the change in t. So all that to say that if we're at time 0, our step size is delta t equals 1, then our next point would be time equals 1. So I want you to imagine that that is the second row in our table up here. Okay, what would be our corresponding y value? Well, our y sub k plus 1 will be our old y sub k. I'll call this guy here y sub k, t sub k. And that is going to be plus our step size times our rate of change, which would be this guy here, the negative 40. And in this case, I'm going to use k1 because it's really the name of the slope that we're using. Okay, so if I took our current value of y, which is 100, and I added the rate of change to it, negative 40, because remember our step size is 1, so it's 1 times negative 40, we would be at y equals 60. Awesome. So that means that over here at time 1, we are now at a y value of 60. Okay, so that would basically say Euler's method would use that as our next point on the solution curve. But we're not going to do that. What we're going to do now is we know we're at the point 1, 60, and we're going to compute the slope at that point. Okay, so that's going to be what is called K2. Okay, K2 is going to be the slope, our differential equation, evaluated at tk plus 1, comma, yk plus 1. And that, once again, is just going to be our differential equation, which is negative 0.4 times y. And I guess I should probably call this yk plus 1, and this is yk over here. So now, just like we would in the second row of our regular Euler's table, we're going to take negative 0.4, but times this guy here. Okay, that would be our slope at this point right here. Remember, it doesn't depend upon t, so the 1 doesn't get plugged in anywhere. But if we had, say, negative 0.4 yk plus 1 plus 6 tk plus 1, then we would also use the 1 plugged in there. But since this only depends on the value of y, there we go. Now we know that comes out to negative 24. Okay, so that's saying that at this point the slope would be negative 24, and if we were to be in the standard Euler's method, we would take the 60 and subtract the 24. But what we're going to do instead is we are going to actually take the average of k1 and k2. So take k1 plus k2 divided by 2, and that is going to be the actual slope by which we're going to change this original 100. So it's as if all we're doing here is we're grabbing a new slope. This is that negative 24 slope. And we know that this slope right here, which is negative 40, is really big negative, and this is a smaller negative. So when we average them together, negative 40 minus or plus negative 24 divided by 2, that's going to be negative 64 divided by 2, which is negative 32. So all that work was just so that we could grab the slope that we will actually use, actual slope. Now keep in mind that it's not really a big negative number, it's not a much smaller negative number, it's the midway point between them. So now, just like Euler's method, all of that work just to compute the slope. So the actual value at time 1 we're going to use is our y sub k plus the step size, which is 1, times the change in, times the dy dt, which is negative 32. So here we will actually get 68 as our y value. Now notice that that's not quite as low. We were really far under because we kept using these really big negative slopes. But now we're actually using the average of a really big negative slope and a negative slope that's slightly smaller, giving us a slope of negative 32. Now we repeat this process. So now we take 0.4 of our current y value, which is 68, and negative 0.4 times 68 gives us negative 27.2. Okay, so already you can see that that is a negative slope, right? But again, what we're going to do now is we're going to advance in time. So if this had been our Euler's slope, we would take our current y, 68, and we would add to that the negative 27.2, giving us this would be time 2 now, because this would be the time 2 estimate of 40.8 as our y value. Now that's not what we're using because we're going to compute another slope based upon that ordered pair. So negative 0.4 of the next y value, which is 40.8, and negative 0.4 times 40.8 gives us negative 16.32. So notice, big negative, smaller negative, we're going to average them together. Negative 27.2 plus negative 16.32 divided by 2. And we get negative 21.76. So notice again, if you look at the second row of Euler's method, what we actually used at from time 1 to time 2 was negative 24. But instead, here we're going to use the average of a big negative and a smaller negative, and we're actually going to change our value of y by negative 21.76. So the actual value will be 68 minus or plus the negative 21.76, which gives us a time 2 value of 46.24. And already I want you to see that at time 2, we were down at 36, but now we're up here at 46. So our error already is, we're still maybe honing in on this point, our error is not going to be this big. So repeat this process. Negative 0.4 of 46.24 comes out to negative 18, we'll just round it, negative 18.5, we'll just say. It's good enough. Okay, so the time 3 value, if we were using standard Euler's method, would be the 46.24 plus the negative 18.5. Okay, so our next ordered pair would be 74. But keep in mind that, again, we are going to use this new ordered pair here to get a second slope, negative 0.4 times negative 0.4 times 27.74 comes out to about negative 11.1. Okay, again, we're going to use the negative 18.5, the negative 11.1. We're going to average those two slopes together. Divide by 2. negative 18.5 plus negative 11.1. Negative 29.6 divided by 2 is negative 14.8. One thing I want you to see again, look at the actual time to slope. It was negative 14.4. And now, I guess we are using something a little bit bigger here. But let's go with it. And so now we are going to, remember this is our dy dt that we're actually using. Our step size is 1. So this would still be delta t times this that's going to get added on to our y value. So we have 46.24 minus 14.8 puts us right at 31.44 will be our estimate at time 3. Again, take negative 0.4 of that value. It's our slope at the point. Comes out to negative 12 we'll just say negative 12.6. So at time 4, if we were to advance to time 4 and this were the rate of change we'd be using, we would take 31.44 minus or plus negative 12.6, which would be 18.84. Okay, now that would be our point. We were using Euler's method, but we are actually going to now get another slope at that point, negative 0.4 of the 18.84, which is about negative 7.54. Just pardon my sloppy rounding here. Sometimes I'm rounding to 1 decimal place, sometimes to 2. But okay, here we are down here. So now let's average our two slopes together. Negative 12.6 plus negative 7.54 divided by 2. Divide that by 2, we get negative 10.07. Okay, so keep in mind, we're always averaging the two slopes in each of these last lines to get our ultimate slope, which is going to be our, again, we're just multiplying by 1 because our step size is 1, which is why we're just adding the negative 10.07 to the 31.44. So 31.44 plus negative 10.07. And the reason you're hearing me say plus is because we're adding a negative, so we are subtracting, but we're always adding the slope. And at time 4, we get an estimate of 21.37. And that is our final answer here as our estimate. And my friends, I want you to notice that our actual y value was 21.19. So when we go to compute our relative error percentage will be our estimate minus our actual, our exact, which is 21.19, divided by the exact, which is 21.19, times 100 to get it into a percent for us. And we get 21.37 minus 21.19 divided by 21.19 times 100. And believe it or not, we noticed we're just slightly over because the slopes that we were adding were smaller negatives than in the standard Euler's method, so we get about 0.85%. Now that is much better. That's a much better estimate, and that's why this is called improved Euler's method. It is better as an estimating machine than standard Euler's method because it utilizes, once again, if we look at this little picture I try to draw here, we calculate a slope at our current point. That's our K1. Well, that's our K1 slope. Then we use that K1 to get the next point at the next unit of time, which was 1,60. We calculated a slope there, and then we took this slope, and we averaged them together to get something slightly in between, right? Something a little bit flatter, because it's the average of a really steep slope and a slightly less steep slope. So the average of them will be a moderately steep slope, if you want to look at it that way. And with all of that, we get a much better estimate. Now, at the same time, just like Euler's method, improved Euler's method is going to have some error. So what we do see is that Euler's method has error in comparison to Euler's for the same step size. However, it still compounds error and does not entirely solve our problem. We will ask an important question next, and we will then motivate Runge-Kutta 4, which uses 4 different slopes and is incredibly accurate even for reasonable step sizes. So Runge-Kutta 4 is going to use 4 slopes. So we've done it with 1 slope. That's why we start with Euler's method, is to get the idea. Then 2 slopes, which is, you can call Runge-Kutta 2, but Runge-Kutta were the mathematicians that came up with Runge-Kutta 4, and it turns out that you can't do much better than using 4 slopes.